And this one on the left will have negative. And negative plus how much depend on the coefficient in the equation. So 1, 1, 1, 1 coefficient. So therefore negative x plus x and plus x. So therefore this becomes 0.045 minus x, and this becomes simply x, and this becomes x. And then we substitute this 3 into the equation, we get this equation. So this again will be a quadratic equation. So this time we have to use a quadratic formula to solve it. Because for this problem, we cannot use a small x approximation to drop this x here, because this Ka is not so small. So therefore, if you time 100 times this Ka, and it will not smaller than this 0.045. So for simplicity, we will write, we don't use the scientific notation for this number, we just write 0.059. So therefore we get this equation, which means we will distribute this number into these two numbers. So therefore we still have x squared on the left side, but on the right side we have these two new terms. Then we multiply, and then we let all the all the terms on the one side, so that we'll get this equation. Then this is the standard quadratic equation, and in this standard quadratic equation we can say a equal to 1, b equals to not negative, b equals to 0.059, c equals to negative 0.002655. Then we can use our quadratic formula to solve it. So it's kind of a tedious problem again, and you want to solve the use the quadratic formula. So we will write x equals negative b plus minus square root over b squared minus 4 times a, then times c, then divided by 2 times a. So we plug in those numbers, and we can see our b is, so negative b, and b is 0.059, so negative 0.059 plus minus square root over, b squared becomes 0.059 squared, then minus 4 times a is 1, c is negative 0.002655, and then divided by 2 times a, which is becomes simply 2 times 1. Alright, so if you do those calculations, and finally you get take the square root, so negative 0.059 plus minus the number is 0.1187 divided by 2. So therefore we take x1 equals negative 0.059 plus 0.1187 divided by 2 equals 0.02985. And if we use the negative sign from the square root, so we can see something like this. x2 equals negative 0.059 minus 0.1187 divided by 2. Then we will get a negative number for x, negative 0.0889. So we will discard this x2 because we cannot have a negative equilibrium concentrations. You can see in the IC table, the x standing for the equilibrium concentration of these two, and it cannot be negative. So therefore, we'll use x1 equals 0.02985 equals H30 plus concentration, and we said we can only use the first ionization to find the pH because the contribution of the second ionization, so the second ionization does produce more H30 plus, but produce so less compared to this number. So therefore, we will just use this number to calculate the pH. So therefore, we will say pH equals negative log 0.02985, this number, and then so that become 1.52. So that's our number for pH. The second part of the question is to find out the concentration of the oxalate. So that will depend on the second ionization. And we can see the second ionization is given in this second equation. So even though we did not use this second ionization to find out more H3O+, we just used the first one to find out H3O+. As we said, the second ionization will give much less H3O+ compared with the first one, so we'll neglect the contribution of H3O+ from this second equation, and so therefore we have the number for the pH already in the last page. But if you want to find out the concentration of this one only appears in the second equation, so therefore you have to use this second ionization. The second ionization will have that Ka2. So this has the equilibrium Ka1, and this has the Ka2. And not only that, when we set up IC table, we'll see the initial concentration of this HC2O41 negative and this H3O1 plus. So the initial concentration in the second step will depend on the equilibrium concentration of this H3O plus and then this HC2O41 negative. So therefore, we will do our equation, the second ionization equation, and then write up the Ka2 for the second ionization, and then we will set up the IC table so as we said before. The initial HC2O41 negative and H3O plus concentration in the second equation is the equilibrium concentration of the HC2O41 negative aqueous and H3O plus concentration in the first ionization. So that means we already find out this H3O plus concentration at equilibrium for the first ionization, and also this the same number for this HC2O41 negative. So therefore, we use these two numbers as our initial concentration for this two, and then we will finish the IC table. So again, there's a 0 here. So therefore, so considering these three numbers, there's a 0. This on the right side. So therefore, we'll shift to right to achieve equilibrium. And then both of these are the reactant, and this is the product. So therefore, this become plus and minus. So this time, we will again examine their coefficient. So we can see the coefficient for this one is 1, for this one is 1, for this one is 1. So this is the equilibrium we talk about here. So we'll use a new name. We'll call that Y and Y and Y here. So therefore, this becomes 0.02985 minus Y, and this becomes 0.02985 plus Y, and this becomes simply Y. So similar, we will substitute these three numbers into the equation for our Ka2. So we have a Ka2 equals the H3O plus concentration times the C2O4 negative concentration divided by the HC2O4 negative concentration at equilibrium. So we just plug those numbers in. The question tells us what is Ka2. So Ka2 equals 6.4 times 10 to the negative 5. And then we plug this 0.02985 plus Y for the H3O plus and Y for the C2O42 negative. and then this 0.02985 minus y for the HC2O41 negative. So get this equation. Now this equation is quadratic, but we can use that approximation. We call that small x approximation. Okay? Why? Because this Ka is very small. So if we take this Ka times 100, so 100 times this Ka, 6.4 times 10 to the negative 5, and we get 0.0064, okay, which is less than or smaller than 0.02985 of the initial concentration of the beginning acid. So therefore, what that means, we can drop the, even though here all small x, small y, just those guys. So here we call the small y. Okay. So therefore, whenever there's a y subtracting to a number or adding to a number, we were just assuming those y is so small compared to those number. So therefore, this number minus a small number as y is still this number. And this number plus a small number, the number is so small, so therefore still this number. Okay? So therefore, this equation become 6.4 times 10 to the negative 5 equals 0.02985 plus 0, because you adding a very small number to that is still the same. So therefore, we don't just really need to adding that number and adding that y, 2985 minus 0. So that means you get these two cancel out, you get y. So that means y simply equals the Ka2, and that's the pattern. Okay. So therefore, and then we see what is y? Y representing the concentration of C2O42 negative at equilibrium. So therefore, C2O42 negative concentration at equilibrium equals to that. So therefore, by compare our initial pH from our step 1, so we said pH equals 1.52, and then our answer will be matching the A. Okay, so the next question is number 10. So number 10, we just want to practice one calculation for the weak base. So give you the initial concentration. So this is the initial. Initial concentration of the weak base, and give you the Kb for the weak base, and you want to find out pH. Very similar as for the weak acid. You first write up the equation. You take the weak base, which is NH3 in this example, plus water, produce NH4 plus, because this base accepts H plus of the proton from the water. So water acting as acid. And we write up the Kb for this above equation. And we have these two products on the top, one reactant at the bottom, water not in because water is the liquid. Set up IC table like that. So again, we see there's a 2 0 here, so that means think about the initial concentration. So the initial mixture will shift to right to achieve equilibrium. So therefore, these two are the product, and these are the products. So this is the rating. So then this is negative. We will assume negative x plus x plus x, and they are all x because the coefficient is 1, 1, and 1. If the coefficient of 1 is 2, then it's 2x. So therefore, this becomes 0.25 minus x, and this becomes x, they become x. So we substitute those numbers into the equation for the Kb. We get this new equation for Kb. And again, this is the quadratic equation. You can solve that precisely using the quadratic formula. And we will always try to use a simple way. So for this example, if we check in our condition, it's okay to use a small x approximation, which means you will drop this x here. You can check that, and let's check that. So we'll take 100 times k, in this case it's kb, equals 100 times this number. It becomes 0.0018, which is smaller than 0.25. So therefore, we can simplify this equation into this equation. Again, you compare this equation with this equation. So here this x disappeared or becomes 0, because x is so small. 0.25 minus x is still 0.25. Now the problem becomes more simple because you don't have to using quadratic formula. So what we said before, this equation becomes 1.8 times 10 to the negative 5 equals x squared divided by 0.25. You multiply the 0.25 over, so you get 1.8 times 10 to the negative 5 times 0.25 equals x squared. And then you just take the square root of both sides. So therefore get x equals the square root over these numbers, that becomes that. And just be careful, you check back into the IC table, see what is x. So you can see in the IC table x representing the concentration of OH1 negative at equilibrium. And you want to find a pH, you cannot use that right away. So therefore, if you take the negative log of the OH1 negative, you get a pOH. And that becomes 2.67. Then we know pH plus pOH is 14, so therefore pH equals 14 minus pOH equals 11.33, so the answer is C. Okay, so the next question, number 11, is conceptual. So we are given 4 solutions and ask which one is acidic. So we will follow these steps. For those given 4 salts, their cations are Na plus, because they all have Na. They all have Na, 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 Na. Their anions are those. So if we take the Na plus from this formula out, for this one we get HSO4 1 negative. For the next one we get HC2O4 1 negative. Then for number 3 we get H2PO4 1 negative. For the last one we get HCO3 1 negative. And they are the so-called protonated anion from polyprotic acid. They can either be acidic or basic depending on their Ka or Kb for them. So if there are Ka larger than Kb, then those anions are acidic. If opposite, if Ka is smaller than Kb, then those anions are basic. So therefore, to answer this question, and we have to find out what are the Ka and Kb for those anions. So for the first one, which is HSO4 1 negative, so if HSO4 acting as acid, then the ionization equation is this. So that means this donating the H plus to water become H3O plus, then HSO4 1 negative become SO4 2 negative. So then this pretty much can say this is the second ionization for the H2SO4, so therefore the Ka for this one, for this equation, is actually the Ka2 for H2SO4, which is given in table 16.3. So 16.3. So this table has those sulfuric acid, and Ka2 is 1.2 times 10 to the negative 2. So therefore, we will see the Ka for this HSO4 1 negative is this 1.2 times 10 to the negative 2. Now, how can we find Kb for this HSO4 1 negative? So we will use HSO4 1 negative act as a base. Then the equation for the ionization will be HSO4 1 negative plus water, Take H plus away from water, become H2SO4, then plus OH1 negative. Then we'll see how likely this equilibrium will be. So we will find out this K, and then this is called KB. So then KB, we know there will be a way to find a KB for those kind of process. So KB for this equation will be Kw divided by Ka of the conjugate acid, which will be this one, and then K, that means the K for this acid will be the Ka1. So therefore, we will use Kw divided by Ka1 of sulfuric acid, and Ka1 from the last table, 16.3, tell just large. Recently, literature value show that Ka1 for H2SO4 is larger or equal to this number. So therefore, we just use this number to the calculation. So Kb for this HSO4 negative become Kw divided by Ka1 of sulfuric acid. So in the table, I did not give to you, but as I said, I find out some of those literature value is this number. So therefore, we find out the Kb for this HSO4 negative is this number. Then we compare this Kb, and then compare this Ka, and obviously that Ka is much larger than this Kb, so therefore this guy, it will be acidic. And then you considering both ions together, so in this first solution you have Na is neutral, then this guy is acidic, so therefore altogether is acidic. So similarly, you will do the process for the next ion, which is NaHC2O4, and then again Na plus is the cation, and which is neutral, pH neutral. So therefore, your solution's acidity or basicity will depend on this negative ion. So this negative ion's acidity or basicity will depend on the Ka or Kb for this. So to find out the Ka for this one, we just write up the equation, use this as acid. So therefore, lose this H, become that. And then we realize this actually is the second ionization of this H2C2O4. So therefore, you use the IC table, use the table 16.3, you get a Ka for this is 6.4 times 10 to the 5. If we use this ion acting as base, so that means this ion accept one more H plus, become H2C2O4. Then water lost H plus become hydroxide. Then we'll say this equation has a Kb. So that equation has a Ka. So then how we find out Kb for this one? Similar to the first question. So Kb for this one equal to Kw divided by Ka of the conjugate acid. So conjugate acid Ka has two Ka, Ka1, Ka2, and you starting from this neutral, you'll see the Ka1. So therefore, the Ka1 for this H2C2O4 will be 5.9 10 to the negative 2. So we take a Kw divided by 5.9 10 to the negative 2, which is the K1 equal to this number. So this will be the Kb for this HC2O4 negative. So to compare this Kb for this one, compare that with Ka for the same ion. So the Ka is larger than this Kb. So therefore, this ion is acidic, and the other ion is Na plus in the solution, is neutral. So therefore, this solution is acidic. So similarly, we'll do the analysis for the next solution, and which will be the Na with H2PO4. So as we said, Na is the pH neutral, so the other ion, the negative ion or the anion is this one. So this one may be acidic, maybe basic, so therefore we have to compare the Ka and Kb. So if this H2PO4 negative acting as acid, so lost another H plus and become HPO4 negative, and then this will have the Ka as written. So now, how big is the Ka? And then we have to realize what is this process. So you already lost H from the H3PO4. So you start with H2PO4, so therefore this is the Ka2 for this H3PO4, which is given in the table. So therefore we just looking at the table 16.3, we find the Ka2. So this equals Ka2 for this H3PO4. And H3PO4 Ka2 equals 6.2 times 10 to the 8. Now, if we use this acting as a base, and we have this equation, and this we see how it has a Kb. So how to find the Kb for this equation? You again use Kw divided by Ka of this acid, and this acid will have Ka1, Ka2, Ka3, so therefore use Ka1. Ka1 from the table is 7.5 10 to the 3, so therefore Kw is this number divided by the Ka1, so this is Ka1. We get this number, so this is Kb for that H2PO4 1 negative. So compare this Kb with Ka, and this Ka is still bigger because Ka is -8, this is -12. So therefore Ka is larger than Kb for this, so therefore this is acidic. And Na is neutral, so therefore altogether neutral plus acidic, so the acidic. So the last one is sodium bicarbonate. So the positive ion again is Na, which is pH neutral. The negative ion is bicarbonate, and we can say this will have a Kb. So if K is larger than Kb, the acidic. If K is smaller than Kb, is basic. We have to find out what is the Ka. So we will use this as acid, and then this becomes this equation. So therefore this equation will have a Ka, and then this Ka will be the Ka2 for this H2CO3. And then use the table 16.3, we find out a Ka. So Ka2 for this carbonic acid 5.6 times 10 to the -11. Otherwise, if we use this as a base, we have this equation, so we'll have this Kb. And Kb again will Kw divided by Ka of the conjugate acid, so this will use Ka1, so Ka1. And Ka1 from the table 4.3 10 to the -7. So therefore Kw divided by Ka1 becomes this. So this will be the Kb for HCO3 1 negative, and then compare with our Ka, which is 10 to the 11, Kb is 10 to the 8, so therefore Ka is smaller than Kb for this bicarbonate. So therefore for this bicarbonate is basic, and we have this solution. In this solution we'll have two ions, so we'll have this Na plus ion, then we have this bicarbonate, and this is neutral, and this is basic. So neutral plus basic is basic. So therefore the solution is basic. The answer you check for question 11 is B. Okay, so the last question is also number 12 is also conceptual, and we are given 5 solutions. They are all like those kind of salt, and you want to determine those salt are basic solution or acidic solution. So we will follow these few rules. Okay, so to find out the acidity or basicity of a salt, we need to determine its cation and anion using the following rules. So if the cation from a strong base, and then they are or cations from a strong base are pH neutral, so the following cations are pH neutral: Li plus, Na plus, K plus, Rb plus, Cs plus, Ce2 plus, Be2 plus, Sr2 plus. You need to memorize them. The second rule is if a metal cation is small in size and high in charge, then it is acidic. So memorize these 3. So Cr3 plus, Fe3 plus, and Al3 plus are acidic. So if a cation is a conjugate acid of a weak base, then it is acidic. For example, just memorize these 2. NH4 1 plus and CH3 NH3 1 plus, so these 2 guys are acidic. And rule number 4 is the Anions from strong monoprotic acid are pH neutral. For example, Cl1 negative ion is anion from HCl, so therefore Cl1 negative is pH neutral. So similarly, again, Cl1 negative, Br1 negative, I1 negative, NO3 negative, ClO3 negative, ClO4 negative. So all those are pH neutral. Memorize. Okay? So then the anions from weak acid are basic. For example, F1